1 and 6.2. So 6.1, basically, we have three more material to cover. We have brick, we have aluminiums, and then lastly is going to be the FRP. So the brick we have just only two type of the brick, and we classify it by its resistant area. For example, the first one is solid brick. So solid brick, you can see that the resisting area is going to be at least 75% of its total area over here. Okay, so if the resistant area is going to be higher than 75%, we call it solid brick. And then if it's in between 40 to 75%, we call it the hollow brick. So the brick is normally manufactured by using the clay, the red clay, and then they just add some more waters in it, and then they just make it like homogeneous, and then they make it into the brick shape, and then or maybe they put it into they put into the mold, and then they just compress it, and then they're going to get the shape like this as shown in the figures, and then they just dry it out for about a few days, air dry it, and then after it hard, they're going to put it into the oven like about 800 degree to 1000 degrees Celsius, and then let it in contact with the heat about like 7 to 10 days. So this is the process to create the brick masonry. Okay, I just call it the red brick. So these are some figures that show the usage of the brick. For example, like the University of the Arizonas, and then the house. One is the single leaf, second one is going to be the cavity walls, and then last one is going to be cavity wall grouted. So the single leaf is going to be the one layer of the brick in order to divide the section of your building. For example, this one is just only the single leaf, because it's going to have just only one layer of the brick. And then for the cavity wall, this one is going to be the one that really good at heat resistant, which means it's going to produce like the air pressure inside like this. Okay, which means this one is going to be, for example, if this one is outside of your house and then this one is inside of your house, so when the heat from outside try to get through the brick, and then it's going to stuck in this location at the middle one. Okay, and then when the heat trying to get into this brick more, so there's no space for the heat to get in, so and then it's going to flow out like this. And then for the internal, if you stay in your house over here, it also can block the air condition, the cold air in your house to go out too. So it's really good for the cavity wall, but the thing is it's expensive compared to the single leaf. To be similar over here, but they provide enough space at the middle in order to add grouted cement. So what is grouted cement? Is going to be some special cement plus water, and then they're going to add some sand in it. Okay, basically this one is a mortar, a high strength mortar, and then they're going to input some reinforcement inside to make it as a wall, reinforcement wall. Okay, clay and the concrete masonry units to specific the pattern and use mortar to bond between the brick, which means masonry basically is the bonding material that going to bond between brick using mortar. Okay, and then mortar, as you may know, we have the ingredient of cement plus waters plus sand. So this one is going to be mortars, as you may know in the labs. But for the silica cement, okay, so silica cement is going to be key compared to the one that we use at the lab. We call it constructional cements. That one is going to provide high strength, a good hydration, and also a slow hydration. Compared to the silica cement, is going to provide a really rapid hydration, and then cream, in order to make a good bond between the brick and the mortar over here. Okay, these are the type of the cement. To classify it, normally we divide into 3 types of the brick. The first one is going to be self-weathering, which means it's really good in resisting the weathers. And the second one is moderate, is in the middle, and then last one is going to be not no weathering. To classify it, we need to classify it by using the strength, the compressive strength of the brick. So the first one, self-weathering or SW, is 20.7 megapascal in compression, and medium weathering is going to be 17.3, and then last one is going to be 10.3 megapascal. And again, for the steel, we're going to use 3 samples to test, or concrete, we use 3 samples to test. If I ask in the examination how many samples that we need to use to test the brick, you need to answer that it's 5. You need to use 5 samples for the brick testing. Okay. The property of the brick, it depends on the type of clay and manufacturing process, and then firing level. The more you put it into higher temperatures with longer time, it also produces a really high compressive strength to your brick. Okay. Parameters, 2 parameters called water absorption and saturation coefficient. I think this one you may have experienced already from the concrete. You test it at the concrete lab, which is the one that you put the brick, weight the brick, and put it in the waters, and then take it back, and then dry the surface out, and then measure it again. That also tell a lot. For example, like if the brick has low water absorption and saturation coefficient, it's going to have less pore, okay, or we call it as low porosity, low percentage porosity. Porosity means the pore inside the brick, which means when the percentage of porosity is low, okay, which make the strength of the concrete, strength of the brick also high. Okay, low porosity, high strength. Okay, and also high durability. Okay, which also mean in contrast that if the porosity, high porosity, the strength is going to drop. Okay, if you compare it together. Okay, because in the brick, as you may know, we have the thing called the water absorption, which means if you mix the mortar and then you place it here, after that you place the brick on top of the mortars, and then to brick is going to absorb the waters from the mortar, and then sometimes it can cause some crack to the mortars, or maybe it cannot be bond as you expected from your design. Okay, so please be careful. The pore in the brick can suck the water out from the mortars, and then the brick, and it's going to reduce the bonding between the brick and the mortars. Okay. And these are the testing standard over here. And we have a few of disadvantage, and then we have a lot of the advantages. For example, like strong and durable, soundproof, high resistant, temperature proof, and aesthetics, and cheap with low maintenance and environmental friendly compared to the steel. But the disadvantage is going to be the time consuming. When you construct the house and then you use this clay brick, it's going to cost a lot of time and also require a really high skill labors in order to construct it. This is the disadvantages. And for the next material, it's going to be the aluminum. So properties, 2 main alloy in mixing, such as coppers and then the magnesium, and then we're going to heat it and then combine it together. So when these two combine together, we call this material as the non-ferrous material. Non-ferrous material basically mean that there's no iron inside the material, inside the aluminum, which means it's really good at the corrosion resistant. Okay, so after we combine it, we call it aluminum, and aluminum we call it as the non-ferrous material with a really high strength, lightweight, and ease of construction, with the high resistance to environmental corrosion and also the some acid. But most of the application is not gonna experience this. Okay, because of its properties that can resist high corrosion. That's why you see it as the material used to build outside in contact with the environment. Shanghai Bank, you can see that they also use the aluminum outside in order to resistant to a harmful as the ultraviolet over here, or we call it just called UV. And also because of its high resistance to the environment, which make this material to have less service compared to the other material, which also can reduce the cost in the futures. Even though the material itself it's a little bit expensive, but in long term it's going to worth it. Okay. And then the manufacturing process of the aluminum alloy, you may have learned this in material engineering. So we have three type of the manufacturing. We have one is extrusion, the one with hot roll. So we blend it together with other alloys and then pull it out. We call it by using heat, we call it extrusion. And then for drawing, we use the one that cold already, and then we're going to pull it. It's called drawing, or we just call it this process as the cold work. And the third one is the forging. This one we're going to reheat from drawing, and then we bend it into any shape that you like to. And the structural shape, we're going to use the alloy number of this that we test at the lab, and then the one that we test at the lab, it's come from the extrusion process. There are three things that I would like you to remember from this. So the aluminum alloy is a high strength material, high pulling strength or high tensile strength, as you can see when you go like this. But it behaves it's behave as the ductile material. Okay, and because of if you compare with the steel is going to produce a really clear yielding point, but for the aluminum alloys there's no clear offset clear yielding point, which means you need to offset 0.02% in order to find the yielding point on this curve. And here's the token, use this table as the reference over here. Okay. Lastly is going to be the fiber reinforced plastic composite. This one may not be really famous in our country, but in our zone, but it's really famous in Europe because it's a material that really good and resistant to the environment. So to form this FRP, we just call it FRP. Okay, we call it FRP composite. This material is going to provide you a really high tensile strength, but in a really maybe 1/3 of the Young modulus compared to steel. But it has a really good metric, it can be used as the reinforcement. If you GFRP bar, if you search on the internet, you're going to see this reinforcement called GFRP bar. It's the one that really famous to use at the ocean area, because this reinforcement is not gonna produce you the corrosion to your structures because it has no iron inside. So the FRP composite is going to have one, we call it continuous strand mat, which is the material at the middle, and then we're going to add the fibers inside, okay, on top and bottom, and then we're going to put the strand mat, another one on top over here. It's similar to the reinforced concrete. So if this one is a section of reinforced concrete, right, we put the steel top and bottom, okay, and then we use that material to, and we use reinforced concrete to resist the tensile force. Similarly to the FRP structures, we have on top over here is the fiber as the reinforcement, okay, and then we have the strand mat over here, and then the surface wheel over here as the concrete. If you compare to the concrete, okay, this one is the cover mat. So they use it a lot in Europe, but not as here. These are some examples. For example, the one that I've seen in Thailand is the one that used to repair the slab, because when there's some cracking on the slab surface, they use the FRP sheet in order to put it here like this, because when the concrete produce some crack, it's trying to pull out like this, and then we use the FRP sheet in order to place it on the cracking zone over here like this to resist the tensile force. Similarly, if you would like to reinforce the column, you can just use the FRP sheet in order to wrap it outside, and then it's going to increase a lot of compressive strength by not increasing the concrete section over here. Similarly to here, if they would like to repair the beam, they can also use the FRP sheet in order to cover it here, which means it also have tensile force. This. So it can form into many shapes like this. And the one that we use in our civil engineering field is going to be the glass fibers. Okay. Our fibers, it's a brittle, it behaves as brittle material, okay, which means when you test it at the lab for the ductile material, it's going to give you some deformation shape like this, okay, but for the brittle material, it's going to go up linearly like this and suddenly just fail over here, go down, which means the FRP behave as brittle material, and it has its behavior as in linear, okay, and then the FRP provide you a really high strength, tensile strength compared to the steel, about 250 to 700 megapascal, but for the fiber it's going to produce larger than 1500 megapascal. And if you compare the modulus of elasticity, you can see that they compare with the steel, which means it's going to have just only like 1/3 to 1 by E steel, which means it's not really stiff enough, you know, to use as a really long structures to reduce the deformation compared to the steel. Okay, and then next, just only it's the glass fibers properties. We have here densities, tensile strength, tensile modulus, and then Poisson ratio, shear modulus, and the elongation. Okay, all right. If we talk about thermoplastic is just a simple plastic. If you burn it, it's going to burn. Like if you burn the plastic, it's going to burn. But for the thermosetting plastic, if you burn it, it's not gonna burn. It's a really high resistant to the fires. Okay, and there we go. These are the properties. I'm gonna go quick over here, and to produce it, as you may see, this one is the mat on the top. Over here is the mat, and at the bottom here is fibers. Okay, so they just put mat and fibers into 3 layers, and then they extrude it, and we're going to get the FRP. So these are the standard for FRP. Here, in conclusion, for the mechanical property of FRP, it's a brittle material and linear elastic to its failures, and it's going to suddenly fail. We call it ruptures, motor failures, and it also produce a really light deformation before it fail. Okay. But okay, to get a clear image, we're going to compare the GFRP, the glass fibers, to the steel in the grade of A36. You can see that FRP is good in 4 points, which are the ultimate tensile stress is higher than steel. The compressive stress is also higher than steel, and then for the flexural stress also higher than steel, and the density also lesser than steel. Okay, it's a really lightweight material. But if we talk about the modulus of elasticity, you can see that steel is going to provide a lot of modulus of elasticity, which good for the long section or long span members compared to the FRP. And for example, like compressive stress, this one also lose to steel. Steel provide the compressive stress 2250 and also the modulus of elasticity and flexural modulus of elasticity. This one is going to provide a better mechanical properties compared to FRP. Okay. Okay. So I want you to read this by yourself. Go back. Okay. All right. So for the advantage and disadvantage of this material, for FRP, it's a really high strength, lightweight, and high corrosion resistant with low thermal conductive, and then electrically non-conductive. And the disadvantage is just only the price. It's really expensive, and then a low modulus of elasticity and not homogeneous material, and then it cannot resist a really high shear compared to the steel, and then its mechanical property is decreased with increasing in temperature. Okay. All right, so we finished the chapter 6, and we're going to move to 6.2 is an extra topic that you may usually see this kind of material quite often. For example, like the concrete masonry unit, or we call it CMU. Okay, this is the image in America, I guess, from the DHI slide. So in America, normally we not gonna do something like us, like beam columns. They're going to use the concrete masonry unit in order to build the wall inside over here. You can see that they pour the grout inside the brick in order to make it as a bearing wall to resist the force. After that, they're going to use the slab in order to put on the wall directly. Okay, so they don't need to have like foam work, or they don't need to have like a really complicated structure like us, like for a reinforcement beam or column. They just use the wall to resist the force. Okay, outside like this, they just pour concrete in to create a wall like this. Okay, this is how they do. So for the CMU product, it's going to use 3 type of the component. We have waters, we have cement, and the last one is fine crushed stone. So this CMU property is going to be really cheap because of the fine crushed stone is the byproduct from the coarse aggregate that you use in concrete lab. You can see that when we buy concrete lab, we're going to get like a really good shape of the stone. All right, but before getting a really big good shape of the stone, they're going to crush it first. You're going to get a really huge cube of the stone, and they put it into the crushing machine, and then we're going to classify into many different types of their size, and then we have the byproduct of that crushing process. We call it crushed fine stone. It's the one that not really good in concrete, but they use it to combine together with the cement and water to produce the CMU product over here. So Normally we're going to use the ratio of 1/4 to 1/8, which means it's 1 cement and then maybe 4 to 8 of FCS, fine crushed stone, over here. And then we also have the TS standard 57 for the load bearing CMU, and then we have TAS 58 for non-load bearing CMU. And normally we have 4 sizes in thickness. For example, starting with 70, 90, 140s, and 190 millimeters. We have the size is the smallest, is 70. This one is 90. This one is 140, and this one is 190. To construct it, we have the hydraulic machine and with the mold. So they just mix. This one is the crushed stone, fine crushed stone over here, and then they're going to mix fine crushed stone plus waters and then plus cement, and they mix it. After they mix it, and then they feel that the cement plastering is fill the crushed stone, and then they just put into this mold and then use the hydraulic pump over here to create the concrete block. Okay, so this concrete block, we have many shapes as shown here, but in Thailand we have just only 2 type in standard. This one is the non we call it load bearing, and this one is non-load bearing, and this big one we call it load bearing CMU over here. Okay, for the load bearing CMU, basically we use it for wall constructions most of the time, and then it's going to provide a really high compressive strength with the typical dimension of 190 by the length of 390, and then the thickness is vary, depends on your application, so you can just pick it, but it fixed in width and length for you, and then the thickness is vary. Okay, for example is this one, they have the concrete block like this, and then they just fill in the grout, which is the cement mortar with specific type of cement, and then just put it inside, and then put the reinforcement inside to the wall. Okay, I guess. But this one is not really famous, to construct, because it requires a lot of good typical drawing. For example, like this, you need to like specify a really specific location of the beam, the reinforcement bond beam, as well as the connection like this. So it's really complicated, and the detail is really hard, and then the mistake usually occurs. So that's why this one is not really happen in our countries. For example, you need to input the reinforcement in here, and then you need to also connect it with here, and then you also have the concrete block that connect perfectly like this. Okay, moisture content. Okay, this one is A, B, C, A, B, C, sorry, this one. So the class A is going to be the good one with low porosity, which means it's going to be a good material for underground work, which means the water is going to get through the class A of the CMU. It's harder than other classes such as class B and class C, and it can be used for both above the ground and under the ground, okay, without any surface protection. But for the class B, we can also use similar thing to the class A, but for the class B, it requires some surface protection and also the waterproofing. And class C is going to use for only interior and exterior wall only, and you are not allowed to use this for the underground construction, just only for the above the ground construction only. For example, like the wall, or maybe for the fence. And it also requires some surface protection as the class C over here. This one is A, this B. If you look at the table from TAS 57 over here, we divide this just only into two mechanical property, which is the first one is water absorption. The second one is going to be the ultimate compressive stress over here. So for the class A, you can see that the class A is going to have a really high strain, about 70 KSC. Class B is 70 KSC, and class C is going to be 50 KSC, which means class C is the what we call is the low grade of the concrete block, and class A and class B provide the minimum strength of 70 KSC with 55 KSC if we test 5 sample. Okay, if we pick 5 sample of the concrete block to test, each concrete block supposed to receive higher than 55 KSC, and with the average force of 70 KSC. And the concrete block type A and type B, the difference is just only the percentage absorption, okay, of waters. You can see that class A is really hard for water to get through because it has less void compared to the type B. So that's why you can see that percentage absorption can reach just only 160, 176, 192 compared to the class B of 208, 224, and 240. And for the non-bearing CMU concrete block, the non-bearing concrete block also has the same dimension for the width and the depth. Okay, but for the thickness, it's going to be smaller than the load-bearing CMU, which start from 70 and then end at 90 millimeters. It also differentiate into two type, but this one changed from TAS 57 to 58 for the non-load bearing CMU. And then we have two type. One is with moisture control content, another one is without moisture control content. But the things that you need to remember when if you in the future, if you are the one who is going to buy it for your company, you need to check that the non-load bearing CMU supposed to have this shell thickness larger or equal to 12 millimeters. Okay, if it's less than this, just reject it. Okay, this 12 millimeters thickness is not this one, right? It's not this one. It's going to be the shell over here, the size of here. Okay, and the other dimension can be plus or minus 3 millimeters only. For example, like this shape, if you measure equal to 9, 3 plus 9, 8, 7, so it's still acceptable for this. Okay, another one we going to look at the strength of the non-load bearing CMU. You can see that even though it's not going to resist any load, but it requires some small amount of the strength resistant force. Because of what? When we construct the wall, we're going to put it at the bottom, right? So this bottom is supposed to be able to resist some load. Okay, so that's why they set it in the minimum of larger or equal to 25 KSC. Okay, and if we test 5 sample, again, if we test 5 sample, each sample is supposed to be higher than each sample supposed to be higher or equal 20 KSC. And these are the advantage. It's similar to the clay brick. the one that we just passed previously. So it's going to be good in a really high compressive strength and soundproof, fire resistant, and temperature proofing material, and cheap with low maintenance and the environmental friendly. But it also require, I think this one may not require a really high skill labors as the clay brick, but it also needs somebody who understand the clay work in order to construct it. Okay, this is this other product. So I think this one in the past, one of your senior who is the owner, who was the owner of the CMU company, they tested at our lab, and then we plotted as stress and strain to see the property. For example, like in his current product, they use 1/9, and then he went to our lab and then he tested in different ratio. For example, like 1/6, 1/7, 1/8, 1/9, 1/10, and 1/11 to see the mechanical properties and the unit weight. And then if after that he received that the more that he put the fine crushed stone, the strength reduced. But for the density, it's a little bit different. When he mix at the ratio of 1/6, the density is low, but when he tests it at 1/7, the density is increased, and then it starts to decrease again after adding more of the fine crushed stone inside, which means 1/7 is going to provide the optimum, the best one, optimum mixing ratio. And then the water absorption increased a little bit compared to the 1/8. And if we compare all the water absorption in the other mix design calculations, you can see that we have the water absorption keep increasing by adding more of the fine crushed stone. And then after that, he compare all of the different in ultimate compressive strength, different in product cost, and then they see they compare both between compressive stress and the divide with the different in product cost. You can see that the one that provide the optimum for his product is going to be 1/7, but this one is going to be cost higher than what he did back at that time, 1/9, but it's going to produce a really good strength compared to the control sample of 1/9 ratio. Okay. Next one is going to be the precast slab. Precast slab, we have two types of precast slab. One is the solid precast slab, which has the solid section like this one. This one we call it solid precast slab, and another one is the hollow precast slab. So for the hollow precast slab is going to be the one that reduce the weight. Why do we need to do this? Because if you remember from mechanics of material, if you have a beam like this and then you put forces like this, the material is going to be bent like this, which means on top is going to experience compressive strength, and the bottom is going to experience the tensile strength. But they would like to provide the hole at the middle, because of at the middle is going to be the neutral axis. Okay, the NA section. When it's when it's in the NA section, so there will be no force. They're going to occur, no stress that going to occur at the middle section. So that's why they reduce the volume of the concrete at the middle and make it as a whole like this. Okay, but the resistance capacity of the force is going to be the same. So after they reduce it, the weight of material, the weight of the precast slab is lower, which means you can transport more of the product to the site, which means you can save a lot of money. You can save the product material, you can save the transportation cost, and you also can save the production cost too. Okay, and for precast slab, we have two types of the precast. We have the first one is going to be precast reinforcement concrete slab, but this one is not famous because it produces a really low strength and high deformation. But the one that really good in practice is the precast pre-stressed slab. Is the one that I tell your friend to go into the front and then hold the cable with me like this, and then we pull the cable like this, and then we cast the concrete inside. This one we call pre-stressed slab. And then when it reaches like 2 days, we're going to cut this PC wire out, the pre-stressed wire out, and then this one we call it precast concrete slab. Okay, this one is going to produce high strength with the small deformation. So there's no trade-off between these two. So this one is going to win, 100% win. So that's why we don't use the precast reinforced concrete. Okay, when we know that the precast concrete is exists. But in order to construct the precast slab, you need to have the beam ready first. Okay, so you need to have the concrete beam over here ready, and then to construct it, it's really easy compared to the cast in place one, because you can just leave the beam, you can just leave the precast slab like this in one piece, and then you can just like leave it, as you may see in here. You leave it by using the crane and then just put it into this direction. Okay, so the direction it's based on the designer. So for example, in this image, the designer meant to put the precast slab in this way. The good thing about this is you don't need to have a lot of formwork compared to cast in place. So you can as you can see, the worker is here and then just point out the direction. Okay, and then you don't need to have like a really messy formwork, in order to put over here to have resisting the dead load of the slab. So this one, no, you don't need to have, you don't need to do it. You can just put the slab over here and then cast the topping inside, on top of the precast. What is topping anyway? So the topping is going to be the material that we're going to place on top of the precast slab. So this one is the precast slab. Okay, if this one is precast slab, after you assembly it, for example, like this, so you assembly it, the surface of the precast slab is not smooth, right? So what we need to do is we need to add the concrete surface about 5 centimeters on top, like this. So this one is cast in place. Cast in place topping. So that topping is the normal concrete. It's the normal concrete plus the reinforcement steel. Okay, plus reinforcement steel in order to resist, or we call it that steel, we call it temperature steel, in order to resist the cracking on the surface. Okay, I think we let me show you what is the topping. I think I come with the shape, and then we're going to spray some water first in order to clean, and then make the surface of the precast fully covered with the waters. And then you can see that we have the steel, small steel inside over here. Oh. You can see that we have a small, this one we call it YMS, which is the small steel with the diameters about 4 millimeters. This one, we call it the temperature steel. Okay, this one, right? As in the lecture, this one is the temperature steel. And then we spray waters like this for about 5 centimeters. So this one we call topping. Okay. I think we should move. All right. So there are a lot of advantages using the precast concrete slab. So we don't need to have like formwork, a lot of formwork. We also save some construction time, and then we can just like continue construction uh, in different sites. So we can like manage the manpower, you know, to uh, any places. And then it's a lot safer than the one with the a lot of formwork. When we place a lot of formwork on the construction site, it also produce a really high risk of getting injured. Also, the last one is going to be the reduction in, it's going to be reduce the noise pollution in the construction area if we use precast. The classification of the precast concrete slab, we have the one we call it solid slab, the one that I just showed you. What you need to know is you need to know the typical size of it. Okay, in the examination I'm going to ask what is the typical size of the solid slab. So the typical size, the T of the slab, the thickness of the slab is going to be fixed at 5 centimeters, and the width of the slab is going to fix at 35 centimeters or 50 millimeters, 350 millimeters, but the length is going to be varied. It depends. Okay, it depends on your span. Okay, and then because this one is the pre-stressed slab, which means it's also has the pre-stressed wire with the diameters about like 4 to 5 diameters in diameters, 4 to 5 millimeters in diameters, and the angle is depends. For example, like this when we construct it, but this one is not a really good image. The good ones you're supposed to have like the reinforcement from the beam in order to lock the precast slab with the beam. Another one is okay, I forgot to mention that for the solid plank slab, normally the span is going to be in between 1 to 5 meters for normal building. I mean the residential house, with the span not higher than 5 meters. If your building is going to be the a big building, or maybe in the, if you would like to build a really long span of the slab, so you can use the one we call it hollow core slab. So the hollow core slab is going to have the span up to, it has a span length up to 12 meters with the thickness starting from 6 centimeters to 25 centimeters in thickness, and it's provide a really high load capacity compared to the solid one. And normally we use it in like a really large building or maybe parking garage building. Sometimes it may not require concrete topping, you know, in a really specific type of work. And last one is going to be or double T precast. This one provide a really good mechanical properties if we use it, because the, you know, the small edge over here produce a really high moment of inertia, which reduce the deformation better than the plank one and the hollow core. But somehow in construction process it's really hard to construct, so that's why they use just only solid and the hollow core only. Okay, these are from TAS 828 over here. We have the mechanical property as shown and how to pick it up, how to use it for the construction, right? So this one we have a safe load carrying capacity, which means it's for only floor load, or we call it SDL, superimpose that load, and another one is live load, is the moving load. Okay, to pick it, normally for the this one is for the solid slab, you require to have the topping, concrete topping of 5 to 6 centimeters. Okay, which means this one they already include the weight of the concrete topping. What you need to consider is just only the floor load and the live load over here in order to pick. For example, this column to the back column is going to have a span. It has a span of 4 meters. Okay, and right now we are in the academic building, which means the live load from the lower, it's around like 600 kilogram per square meters. Okay, and if I look at the floor material, it's a ceramic floor. So the dead load of the ceramic floor is going to be around 120 kilogram per square centimeters, like this, which means my slab is going to use the 4 meters. My beam span is going to be using 4 meter span, and with the live load of 300 and superimpose the load of 420 kilogram per square meters. So in total, this one is going to be 420 gram per square meter over here. What I need to look at is I need to look at the span, but why the span of 4 meter over here does not have in this catalog or this table? Basically, if you look at this image, I don't know if I have. Oh. Okay, if you look at this image, you can see that if the span here to here, as what I said, is 4 meter. Okay, center to center is 4 meter, which means we need to leave some gap in order to put the reinforcement steel over here. As I said, that we're going to put it in the beam in order to lock, and then we bend this one and then to lock the position of the precast slab over here, which means normally this one is RB9. Okay, so it's about like 1 centimeters. Okay, and then it seems like if my beam span is 4 meters, I need to choose the one with the span of 3.95. Okay, which means my precast is going to be 3.95, and then I'm going to put the reinforcement steel to lock, as we have discussed, over here, to lock the position like this. Okay, and then my center to center is going to be remain 4 meters. This one is going to be 4 meters, and I have the gap of error about 2.5 centimeters for the error adjustment from here. The edge here is about 2.5 centimeters. This is how that's why the size or the length on the table is shorter than your span. Okay, and then right now I already chose 3.95, and then my safe load is going to be 420 kilogram per square meters. I need to choose this one. Okay, and then when I order, I need to tell them that I'm going to use the one with 7 PC wire and each diameter has the each wire supposed to have the diameter of 5 millimeters in diameters. So please choose the correct one. If you choose it wrong, for example, if I choose 350, so it's going to be less than 420. So it's going to produce a lot of cracks, when you construct it. Next one is going to be the cross-sectional of a dimension. This one I already mentioned that you need to remember it. This one, 50 millimeters and 350 millimeters in width, and it requires topping about 5 centimeters, and with the temperature steel, or we call it wire mesh steel, at least with the spacing of 250 millimeters or 125 meters. And the concrete that used to produce to make a slab, it's supposed to have at least the compressive strength of 350 at 28 day. And then when you cut the pre-stressed wire, your concrete supposed to have the target strength at least 245 KSC, and the pre-stressed wires supposed to have the tensile stress or the ultimate tensile stress of about not less than 1750 megapascal, and its material supposed to follow TS 95. Okay, the next one is going to be the hollow core. Similarly, so the difference is just only the strength over here. For example, this one's supposed to have a really the plank, or we just call it the solid one. It requires just only 350, but this one requires 400 KSC. And the topping, they also specify the strength at 210. And we use the same TAS 95 for pre-stressed wire. Okay. Other than that, just select the correct one. For example, the hollow core, sometimes we don't need topping, so you can just use 0 topping as selected to select the material. If you're not gonna use topping, you choose the top table. But if you have topping of 5 centimeters, you choose the bottom table. Okay. To calculate the self-imposed service load, just similar to what I have shown. Right, this one is the example of the testing precast PC slab in our lab. According to the thickness of the slab, it's about like 10 centimeters, which means the unit weight of the concrete is 2400 kilogram per cubic meters. And if I would like to get the safe weight is going to be 240 multiplied with the thickness. So it's going to be 240 kilogram per square meters. And I have the live load, or we call it design load, assuming using it equal to 300 kilogram per square meters. I'm going to add everything together. 1.7 is the load factors. This one also load factors. Load factor for that load. And this one, 1.7, is load factor for live load over here. After I calculated, just sum everything together, I get W equal to uniform load equal to 720. And then calculate the maximum moment by using WL square divided by 8. I'm going to get the moment of 810 kilogram meters. And then I'm going to find Pmax, which is equal to 1620 kilogram over here. And then I need to check the deflection 24 hours after pressing it, and then 24 hours after releasing the load. So when this one is in the loading phase, my slab supposed to have the deformation less than L square over 20,000 H. And after releasing it, the delta 2 supposed to return back at least 75% for RC slab, but we're not going to use this. It's supposed to return back at least 80% of the PC slab, okay, in order to pass that requirement of the deformation. So we check the load, and then we also check the deformation. Okay. And of course, when you go to your cooperative education, I think one of you here will experience this kind of precast slab, and sometime your senior is going to tell you to, to tell the laborers in order to store the precast correctly. If you store the precast incorrect, it's going to produce crack on the surface of the precast. So for a good practice, you need to place the support, the wooden support over here in the distance between 0.5 to 1 meters. If you use on the left side at 1 meter, so on the right side is supposed to be 1 meters. Similarly, put the support over here. Okay. And then if you store it like this, so it's not gonna produce any crack to your slab. So this is a really good practice for a good alignment. So these are some details, you know, in order to construct it. We have like steel beam, RC beam with support, H beam, and the cantilever slabs. Next one is going to be the precast RC and PC pile. So for the precast pile is the most popular one nowadays because it can carry a lot of capacity and it's really fast in construction compared to the the one we call cast in place pile. Okay. Its length, it can be manufactured in the length between 3 to 21 meters, and the safe load that it can carry is starting from 0.5 ton to 40 ton. Okay, and it can be produced in two types, which is the one is RC and another one is PC. But RC, as we may know, it's not really that famous to construct it because it low strength and high material cost compared to the PC one. It's going to provide the really high strength and high deformation. So these are some shape. So this one we call it I shape. I shape. This one is a really good one. And another one we call it I don't know, we call it like load resistant. But for the I shape and S shape, it's going to produce a really high capacity compared to the others. Okay. And if we divide the concrete pile into three groups, we can divide it into pre-stressed concrete pile, bore pile, and the pre-stressed concrete span pile. So what are the difference? So for the precast concrete pile is the solid column, like this shape is the solid shape, column shape, and then we manufacture it in the factories, and then we ship it to the site, and then we can just put it into the ground rapidly compared to the bore pile, and it can be driven into the foundation, into the ground by using the pile hammers. For example, this one. Okay, you can see that this one is the precast pile, and then we have the hammers on top, and then we're going to release the force. We're going to release it, and then it's going to put some impact load on top of the pile, and then it's going to be under the ground. Okay, like this. The I cross section is the popular one. Okay. All right, and then these are the section. We have, even though if it is like I section or S section, this one, we're going to assume that it's going to have a similar dimension for both sides. Okay, for example, like this one, even though the surface resistance is not full, for example, this I shape, when we calculate it, we assume that it's has the square shape like this. That's why you can see that we're going to, even though it's I or S shape, we're going to have just only one size over here. Okay, we assume that both sides are equal. And then we have the perimeters, sectional area, unit weight, and the maximum length over here, and the safe load. Okay, safe load is going to divide into two parts. One is from the concrete, one is from the soil. So this one you're going to learn it in foundation course with Ajahn Phonpon. Foundation course. Okay. And if you move to the bore pile, it's a lot different from the driven pile. So driven pile, it seems like you use the pile and then you trying to push it under the ground like this. But for the driven pile, it's another different story because you need to make a hole like this and then get the soil out first. Make a hole and then get the soil out, and then pour the concrete inside, and then put some reinforcement and pour the concrete in, back in. So that this one we call it ball pile. Okay. So the ball pile we divide into three types. The first one is going to be the small diameter ball pile. Normally we use the small machine over here in order to get the soil out, and then put the reinforcement in, and then pour the concrete in later. This one is good for a small diameter in between 35 to 60 centimeter with a depth in between 18 to 23 meters. And this one we call it dry process. Another one we call light diameters ball pile is the one that we use in a really big construction or a high-rise building construction project. But this one you need to, because it's deeper than the small diameters ball pile over here, so it's starting from 25 to 65 centimeters, and sometimes it can reach around 100 meters for the light diameter ball pile. It starts from 80 to 150 centimeters, and sometimes it can goes up to 2 meters or approximately 200 centimeters. Okay, for the light diameter ball pile, we use the process called wet process. Okay, for small diameters we use dry process, and the wet process we use for the large diameter ball pile. Okay. But this large diameter ball pile, you need to be careful a little bit. If this is you and this one is underground, and then you try to, you know that under the ground we have a lot of types of soil. For example, if this one is clay, this one is sand, sometimes this one is clay, this one is sand. Okay. When you try to get the soil out over here, when you would like to construct this wet process, you need to dig the soil out. Okay, get the soil out. When you would like to get the soil out, what happened is the clay layer is going to stay still. Nothing happened with the clay layer, but the problem is going to occur at the sand layer. Okay. As you may know, the sand is going to be like this. It has no cohesion to it, so it's not sticky like clay. So what happened when you dig the soil out? The sand is trying to flow from a layer to the bottom like this when you make a hole, okay, according to the gravity. So that's why we use the bentonite slurry, which is the what we call the adhesion additive, in order to maintain the sand layer without in order to maintain the sand layer without falling out like this. So when we put the wet process, we just put water in, and then with the bentonite slurry, so we pour the bentonite slurry in, and then we dig the hole like this, and then the slurry is going to run through the sand layer over here to protect the failures of the hole. Okay. Okay. The good thing about the ball pile is just it produces a really small vibration, and then it's not gonna produce a really loud noise compared to the precast. Comparing to this, because when you use the hammer over here, it produces a really loud noise, and it also produces some vibration to someone that stay close to your project. And then sometimes the house maybe experience some crack according to the vibration to the house. So that's why, like in Bangkok, most of the time when there are a lot of houses close to your property, they normally use ball pile instead of the driven pile, even though the driven pile is um, cheaper, but they have no choice. They need to use the ball pile only. Okay. And next one is going to be the pre-stressed concrete span pile. This one is a hybrid between ball pile and the driven pile. Because of this one has a really high density, a really stiff pile. So this one is a really hard pile, which can be used for driven pile like this, or you can use it by the ball pile method like this in dry process. So it can be used for both. Okay. This one, it has the diameters in between 20 to 100 with 6 to 18 meters. And then the wall thickness of it, it's going to be in the range of 6 to 14 centimeters. It depends on the wood. But this one is not famous right now. What I want you to focus is just only these two, pre-stressed concrete pile and the ball pile. Okay. Normally used to drain waters, such as the one that stay under the highway. It has the diameters in between 300 millimeters or about 0.3 meters up to 1.5 meters with 1 meter long for each pipe. So it produced by using a really low slump concrete with the accelerating admixture, which is make it hard quicker than normal, and then with a really low slump to have a really high strength to produce a really high strength concrete. Why do we need to use a really high strength concrete into the concrete pipe over here? Because it has a really low slump and it's require a really quick harden. That's why we need to use a really high frequency vibration machine in order to compact it to become this shape. Okay. And next is going to be type of the concrete pipe over here. We have one is the tongue and groove, and the second one we call it bell and pivot. But the one that famous in Thailand is going to be this one. But we also have this type too. Type. Like this. Okay. All right. So we have this one is RC. This RC. RC is reinforced concrete. Okay. From TS1T8, we have the maximum compressive concrete load and crack load over here. Basically, we're going to test it similar to split tensile test, as you may know if you test it for the cylinder. We're going to test it like this by putting some strip on top and bottom like this, and then we simulate the impact load on top like this, and then we try to press it. Okay, when the load apply over here, we measure when it crack is for 1 parameters, and then after it fail is for 1 meter is the maximum load over here. Okay, so these are the minimum resistant force for concrete pile over here. Okay, what we need to test is we use that pipe over here and then put the strip on top and then apply the load in 7 to 37 kilogram per centimeters per minute over here. And we have the one with RC and another one is without RC, but normally we use the one with RC because this pipe normally going to experience some extra load from the soil. When we construct it, there will be we construct it under the ground, which it's going to have some load from soil, which means we better choose the thickness. We better choose the one with RC rather than without reinforcement over here. And this table show the diameters with the length. Normally, the concrete pipe, it has the fixed length of 1 meters. Fixed length equal to 1 meters. 1 meter over here. And there are like many type in order to construct it. For example, the impermissible as shown in the figure A on top over here. So the pipe lay to the position and it's covered with the compacted soil. So on top over here is compacted soil. Okay. And the ordinary is shown in the figure B, where the soil at the bottom of the pile is just the shape for about like 0.5 of the BC over here. So it depends on the the construction in the drawing later. Now we have another one is the first class, is the figure C over here as shown in the figures. And last one is going to be the best one, that if possible we would like you to construct the concrete pipe under the ground as this by having the concrete cover over here, which the pipe is supported by the layer of the RC and at it half diameters, and then we're going to use the sand and or soil to put on top, okay, to compact it. And here are the properties over here, and that's it for